Hi everyone. In this video, we're going to go through the first section of Chapter 6. Chapter 6 is called Orthogonality and Least Squares, both things that we will be introduced to as we move through these sections. And 6.1, we get a lot of introductory vocabulary, inner product, length, orthogonality. Some terms will be familiar as we move through this section, depending on what math and physics courses you've taken in the past. And we'll start out with something called inner product, but it's better known as dot product. That would be more familiar for sure. So if I have two vectors, u and v, their product, it's not correct to multiply u and v, so we define this thing called dot product, and we can't multiply them because the rows and the columns, right, that has to match up in that specific relationship, so we can't take u times v. We define the dot product, u dot v, as the linear combination of the products of the entries, right? But if we write u transpose, right, the transpose of u like this, like write it horizontally, I can multiply u transpose times v. So this is a regular product, and that is defined. But we also have the dot product that, again, you've seen in some courses in the past. But it's the product of the entries written as a linear combination and added together, right? So that's something that should hopefully be familiar. Okay, so let's look at a quick example here where we take and we want to find the dot product u dot v, and I'm going to write that as u transpose times v, right? That's a regular product, not a dot product. So u transpose minus 2 minus 5 and 2, and then we're going to multiply that by the v matrix, or the v vector, -3, -2, and -3. And you can see how now I can do my regular row-column multiplication, but that is just -2 times -3 plus -5 times -2 plus 2 times -3. And when you do that, let's see, the multiplication here, I get 6, I get 10, I get -6, so that dot product is equal to 10. All right, now for v dot u, that is v transpose times u. If I transpose v, -3, -2, -3, and write regular u, -2, -5, +2, what you'll see if you expand that out, -3 times that should be a 2, plus -2 times -5, plus -3 times 2, well, that also equals the 10 that we got just a second ago. So that dot product is commutative. We've said that in the past. Now we're seeing it again, and we're writing it just a tiny bit differently as a u transpose times v, just to kind of conceptualize it that way. Our next slide here contains the first theorem, which should be all concepts that are familiar. The first one is the commutative property of the dot product. The second is I can take a dot product and distribute it over a sum of two vectors. The third, I can take a scalar times a dot product and multiply that scalar times the first vector or the second vector first, and then compute the dot product. And then letter D, a dot product of a vector in itself is always positive, and it's equal to 0 if and only if that vector is the 0 vector. So u dot u will never be 0 unless u is the 0 vector, but u dot u does have to be positive or 0, always positive or 0. And then if you combine properties, I think it's B and C multiple times over, you get this this equation, this formula that has various, the text refers to it as a, quote, useful rule. I don't know that we'll necessarily use it very much, but it's good to be aware of. Okay, now we get to the topic of the length of a vector. The length of a vector, you've probably seen this before. Length, also known as norm, also known as magnitude of a vector, is the square root of the sums of the squares of the components. That's the technical, the fancy formal way to say that. I could also think of it as the square root of v dot v, the square root of each component squared and then added together. Again, if you've found lengths of vectors in the past, this is the same formula. Notice the notation here. We have two lines around, two of those absolute value lines, but they're not absolute values, but there are two lines around the vector on either side. But this is the formula that we use to compute lengths of vectors. So in an example here where we find length of a vector, we are given a vector v. Notice v is in R4. It contains 4 entries. And we want a unit vector. Unit vector means it has a length of 1 unit. And a unit vector u that points in the same direction as v. Okay, so the way that we do that is we're going to take v, u is going to equal v divided by its length. V divided by the length of v produces a unit vector that points in the same direction. All right, so first we need to find the length of v, and to do that we take the square root of 1 squared plus -2 squared plus 2 squared plus 0 squared. And let me just finish that square root sign there. There we go. So that would be the square root of 4 plus 4 is 8 plus 1 is 9, which is 3. All right. So u is my vector v, 1, -2, +2, 0, divided by 3, which is 1/3, -2/3, 2/3, whoops, and 0 for the last entry in that vector. Okay, so that vector points in the same direction as v, but only has a length of 1 unit. This next example is stated a little bit more formally, but is the same idea as the previous question. W is the subspace of R2, so we're in 2 dimensions, but it's a subspace spanned by 1 vector. So think to yourself, what does a subspace that is spanned by 1 vector look like? Well, it's a line through the origin that points in that direction. We have to find a unit vector z that is a basis for that subspace. Ultimately, here's a vector. Find a unit vector that points in the same direction, that's still in W on that same line. Okay, so what we'll do, and we'll call this, or it tells us, excuse me, to call that unit vector z. So what we'll do first is we're going to call a vector y, and I'll write down the vector 2, 3. All right. Y is still in the same subspace. How do I know that? Think about where I came up with y from. I multiplied x by 3. Each entry in x, I multiplied it by 3. I scaled x, so I'm still on the same line. And what I've done is really just made it easier to find the length to write this as a unit vector. So now the length of y, this temporary vector, is the square root of 4 plus 9, also known as radical 13. So now I can say that my unit vector z is equal to 2 over radical 13, comma 1 over root 13. And so that is my unit vector. That is a basis for W. I know it's a basis. Clearly, it's linearly independent. It's only one vector, and it's not the 0 vector, and it still spans my subspace. It's still on that same line. Okay, now we get to distance in Rn in any number of dimensions. If I have 2 vectors in Rn, the distance between them, notation-wise we write it as dist parentheses u comma v, the distance between u and v, is the length of u minus v. So there's your formula right there. The distance between 2 vectors is the length of the difference between the vectors. All right, now we get to example 4, where we have to calculate the distance between 2 vectors u and v, where u is equal to 7, 1, and v is 3, 2. So 2 steps here. First, we find their difference, the difference between u and v. U minus v is equal to, and I can even write this vertically if I wanted to, 7, 1 minus 3, 2. It kind of lines things up a little bit nicer. And that is 4, -1. So that's their difference, that vector. And then the length of that new vector, the length of the difference, or the distance, is the square root of 4 squared is 16, -1 squared is 1. So radical 17 is the distance between those 2 vectors. I'm not going to go through an example of this in 3 dimensions, but we can also measure distance in 3 dimensions, or in n dimensions for that matter. You take the difference between each entry squared, right? Whether you have two dimensions, 3 dimensions, n dimensions, u1 minus v2 squared, u2 minus v2 squared, etc. The square root of the sums of the squares of the components. In this next slide, we're going to define what it means for two vectors to be orthogonal. When you see the word orthogonal, think the word perpendicular. That's, your middle school, high school word. Orthogonal is your college word, but it's really what we use specifically in reference to vectors. Two vectors are orthogonal to each other if u dot v, if their dot product is equal to 0. Okay, if you check their dot product is 0, that means they're orthogonal. That means that they form a 90-degree angle between the two vectors. Add a little bit more to the concept of orthogonal. We get to talk about the Pythagorean Theorem, something that you've heard about probably in every year since, middle school, right? When you get introduced to the Pythagorean Theorem, still applies in linear algebra. Two vectors are orthogonal if and only if the length of u plus v squared is the length of u squared plus the length of v squared. That's what the Pythagorean Theorem looks like in linear algebra class. The next topic in orthogonality is a little bit more involved. It's something called orthogonal complements, and I'll write out the concept of kind of how this builds. Okay, so if I have a vector z, right? If a vector z is orthogonal, is orthogonal to every vector in a subspace W of Rn, then Z is said to be orthogonal to W. Z is said to be orthogonal to W. Okay, so you don't have to be orthogonal to just one vector. You can be orthogonal to a whole set of vectors, a subspace W of Rn. Okay, then the set of all vectors Z, the set of all vectors Z that are orthogonal to W is called, okay, so here's the term that we'll use here, is called the orthogonal complement of W. And it's written W with a superscript of a perpendicular symbol, and we say it out loud, or one way to say it is the orthogonal complement of W. Another way to say it out loud is W perp. Not pep. W perp. It is the orthogonal complement to W. So if Z is orthogonal to every vector in my subspace W, it is orthogonal to W, and then the set of all of those vectors Z that are orthogonal to W, called the orthogonal complement. For example 6, there's not a lot to do. Just take a second and read through that. Right, we're in R3. W is a plane in R3. And when it says at the end of the example, see figure 7, what it really should say is see my awesome drawing of figure 7. So here is my subspace W, my plane in R3. And here we'll identify this guy as the 0 vector. Let's see. And Z... if Z and W are non-zero, that is Z is on L. L is my line through the origin. So let's draw a line. We'll change colors here. Draw a line through. Oops, I missed. A line through the origin. Okay, I didn't really try to go out the corners of that box. Think of that as passing through W. So like technically this part should be blue because that part of the vector would be behind W, right? So there is my line L through the origin, and Z is some point on L. Z is right there. I have a, let's see, and I'll even make another vector, a little w there that's in W, right? This is a 90 degree, a right angle right there, right? So Z is, Z dot W would be 0. That's what it says there, right? They are orthogonal to each other. Any vector in W, even if I use subscripts, there's W1, any vector in that subspace, W2, that should be lowercase, that would also be orthogonal, that would also be perpendicular to the line L and orthogonal to Z. And just to add 2 more points onto this idea, a vector x is in W if and only if x is orthogonal to every vector in a set that spans W. So it's got to be orthogonal to every vector. That was why I was using the subscripts there. Any W that I pick in there, W1, W2, W3, right? That would be x would be orthogonal to all of those vectors. And then W perp is a subspace of Rn. Okay, we could show that. We're kind of given that information here in the section, though. This next theorem here is pretty cool because it relates orthogonality, which again you may have heard of in the past, to the row and null space and column space of a matrix, which is, you may not think that those things are related, but they absolutely are, which is kind of cool. So if we have an m by n matrix, the orthogonal complement of the row space is the null space. And the orthogonal complement of the column space of A is the null space of A transpose. And those relationships right there are established. So how are those, it's kind of weird, how are those things actually related to each other? And how are they orthogonal to each other? Well, we'll see that, why that is the case in the little proof that we write up here. So let's go through a proof. I'm sure that's what you were waiting for, the first proof of the chapter. Very exciting times. But let's take a look. And again, this will show you how those things are connected to each other, and that's kind of the significance. So if x is in null A, whoops, forgot my L. If x is in null A, if x is in the null space of A, then x is orthogonal to each row of A, to each row of A. Oh, well, why is that true? That is true because, that's supposed to be an arrow, because AX equals 0, right? The null space is the solutions to the solutions to AX equals 0. Those are the vectors in the null space. And how does AX equal 0? How do you multiply A times X? Row by column. So if X is a column vector, then each row of A times that column equals 0, right? That's the definition of orthogonal. The dot product is 0. When you multiply them, you get 0. So those are orthogonal to each other. Cool. So we have a little bit more to say to kind of complete this part of the proof. Since each row of A, I'll say the rows of A span the row space, X is orthogonal to row A, to the row space. Now, we technically have to prove this in the other direction because we're saying it's an equality. We have to show it both ways. Okay, so we'll say, let me just draw a little line here. Conversely, if X is orthogonal to the row space, if X is orthogonal to row A, oops, that should be a capital R. If X is orthogonal to row A, then it is certainly, we'll say certainly, orthogonal to each row, of A. Hence, we have our conclusion. Hence, A times X equals 0. So we just had to, it seems like it's the same thing twice, just in the opposite order, and it is. And because the steps follow sequentially, we just have to formally state it in both orders for this equality to be quote unquote proven true. It has to be true in both directions, and it is. Okay, and then the last little bit to this proof here says, as the first statement is true for any matrix, it is also true for a transpose. So the row space of A transpose is the same thing as the column space of A, and the row space of A transpose perp is equal to the column space of A perp, which is also the null space of A transpose. There we go. All right, so that is the end of that proof. This is the end of section 6.1. Thank you for watching the video. Start some homework problems. Let me know if you have questions or if there was anything that was unclear in here. Have a great day.